Okay, so let's begin today's class. So first, there are some announcements. So you might have received the email that the class website is changed. Okay, so this is uh, this is the original website. So now I provide the link to the new website. So if you click, okay, so this is a new version. Okay, so the main difference is, okay, so now basically I'm going to type all the homework here. So I already fixed the homework 3. Okay, so now the due date changed to next week. Okay, so I'm going to fix homework 4 and 5 today. Okay, so you should click into your homework. Okay, so here I will type the homework for you. Okay. Okay, so you can also check the book because there are some different versions of the books, even for V2. So, and also sometimes I make the homework shorter than the original version. Okay, so please just click into the homework and do the homework. Okay, and if there's a figure, I try to provide also the figure. Oh, this is slow here, so let's. Okay, you can now. Okay. Okay, so that's the first thing. So the homework I will type here. So you don't need to just look at the problem number. Just click into the homework and work through the homework. And second, we change the exam day because there are many exams. There are also the exam for the quantum mechanics and electron dynamics around that week. So we will delay our exam 1 to May 7th. Okay. And then I will put the topic will be covered in the exam 1 here later today. So basically, we'll go from 1, 2, 3, 4, and 6. Okay, so basically, I think we should cover up to chapter 6, but I will provide more details here. Okay. And then starting from today, we'll also spend some time to kind of review some of the homework problems. Okay. So in general, if you have a question about homework that you couldn't figure out how to do, so after the deadline of homework, okay, you still cannot figure out, okay, so or you have a specific problem about a certain section of the book, then you can email me. I can try to explain more in the class. Also, if you want to talk to me in person, then due to this pandemic, then please just email me so we can set up a time. Most likely, we will use some kind of online meeting application. Okay, so we can have a face-to-face over the internet. Okay. Okay, so okay, so let's start today. So in the first homework, you should encounter this formula, Stirling's formula, that is very important for the StatMech. Okay, so basically the result is n factorial is something like 2 pi n okay. So from here, then we have log n factorial is something like n log m minus n plus 1/2 log 2 pi n. Okay, so usually n log m minus n is enough. Okay, usually this is enough. Okay, so then it's very easy to get this simple result by integration. Okay, so you just consider what's the log n factorial, right? So log n factorial is something like log of n multiplied by n minus 1 to 1, right? So that means I can write this as a summation. So this is a log n plus log m minus 1 plus log m minus 2 up to log 1. So let's just write this as a summation. M equal to 1 to n log m. Okay? So now I want to connect this to an integral. Right? So I can think about this is a certain integral from 0 to n dm. Right? So I can think about this here. This dm is 1. So I can put 1 here. I can think about this is a dm. Right? So then in this way, then I can think this is nothing but the log n integral from 0 to n. Okay? And this integration is easy, so it's n x log x and 0 to n. Okay? And so this is, sorry, minus x. Okay? And this will be n log n minus n. Okay? So here you should check that this, when you put 0, then you got 0. But that you can check. Okay. So then we want to how the exercise is for you to get a slightly better feeling for this extra term, extra correction term. Okay, so what's that? Okay, so how do we convert this? So basically, if I have something like this, this is my function of fx. This is x. Right. So we know the integration of fx is the area under the curve. Right. Okay. Okay, so now if I have a discrete version, so then I may have summation is something like that. So something like that. No. Okay. So this is approximate. Then this is basically the area of the bar. Okay. Okay, so then we can use sorry. Okay. Okay, so now let's do something and also plot the curve to see what that means. Okay. So now I use a simple numpy scipy to get this. Okay. So this is a Python. Okay. So I can write a simple function like this is log of factorial, right? So that's what I write. So if log of n factorial is basically the summation of log of n. Okay, and you can have the two different a simple version of Stirling formula n log n minus n and n log n minus n plus this 2 pi n divided by 2 log 2 pi n divided by 2. Okay, and then let's try to this so the difference between those two formula is this extra correction term. Okay, so let's call this diff. Okay. And also if you use this library, so SciPy, they also have a factorial function. Okay, and this is a more generalized. So basically, in this calculation, they use the integral representation. Okay, so they can. Okay, so let's just do a simple exercise that if n is 1 or 2 or 4 or 50, then you can use this log n factorial using this SciPy library, and also if you just take this log n factorial as a sum of log n, okay, so you can see those two agree, okay, and just as a check. Okay, so now if you this crude version, so this is a crude version of Stirling formula. Okay, so this is a number. Okay, so and here this is the one with the correction term. Okay, so you see this error is larger for smaller n. However, if you go to n like 50, already this is the term, the expression with the correction term is very close to the exact one. So this 148.477. This is 1.8.476. Okay, so this relative error is already very small. Okay, so in a way we can treat this one as an exact. If we want to estimate the error for this simple Stirling formula, we can estimate it by the difference between the simple Stirling and the more complex Stirling formula, which is this extra log term. And we want to calculate the relative, so let's divide by the simple Stirling formula result. Okay, so this is sort of difference between those two results divided by this result. Okay, so for small n, we see this this is big. Okay, so now but you go for n equal to 50, this is extremely small already. Okay. Okay, so if you use this, if you just use this plug into very big n, it's going to fail. Those two formula cannot do well for large n. Okay, because the number is too huge. However, you can still use this if we agree that this is basically like exact, right? If I only keep like 5 significant digits, then those 5 significant digits are exact, right? Okay, so basically we can see the difference between those two. Okay, actually, if you only plot the few numbers, they will look the same. Okay, because this number is 10 to the 25. However, the relative difference is 10 to the 20 minus 25 for this 2 10 to the 23. Okay, so this is a very extremely good approximation. So this is sort of the relative estimate the relative error. Okay. So what's the meaning of this summation and the correction term? So this blue line is our integration. Okay, so if I have an n factorial, okay, so our number for log n equal to 1, 1 factorial is 1, so log of 1 is 0. And 2 factorial is 2, and log 2 is this number. Okay. So the area below the green horizontal bar is the actual log n factorial. Okay. And this blue line is our continuous function log n, right? So if I do the integration of this, basically I get the area under the curve, right? Okay, so you go to infinity. Okay, so suppose I go integrate up to n equal to 5. So this is would be this area. Okay, and we see that it is smaller than the log of n factorial. Okay, so that this sort of a triangle part is the difference. Okay, so how do I estimate the sum of those triangles? Okay, so you can double it. So if you think about this, is just put a straight line here, and you put the double. So this 2 times this triangle is about this rectangle. Okay, and 2 times this triangle is about this rectangle, and so on and so forth. Okay, so now if you move this rectangle to here, then and so this the 2 times error for n between 1 and 2 is this, and between 2 and 3 is this. So you move this to here. So this is the error between 1 and 3. So now you can keep going. So this total green rectangle is the area, is the sum of all the errors. Okay, and this will give you 1/2 of log n. Okay, and but there's also another here, so you have to make this difference. This is another term, so let's go back to. Okay, something like that. So you sum all the errors, you get this one. Okay, so this one is 2 times the triangle is about log n, because this is log n. Right, so that means the area of the triangles is 1/2 log n. Okay, so the correction term is 1/2 log 2 pi n, which is 1/2 log n plus 1/2 log 2 pi. Okay, so you can say this, so you can imagine that this area will be roughly about this. Okay, ooh, something wrong. Wait. Okay. Okay, so that's how you do the connection. Okay. So that's the main point of sort of this formula. Okay, so if you want to do a more systematic derivation, what you need to do is you can check other book. Okay, so that you can do usually what you to derive this is you start from an integral representation of the factorial function. Okay, you start from a function. You start from an integral representation, something like this. This is exact. You can check this is n factorial. Okay, so then you can do the expansion. Then you can go get other all kinds of expansions. Okay, so now another homework is about using this delta function. Actually, okay. So basically, we define this omega function as dp dpu. Okay, so we mentioned that if you use a delta function, then this omega function you can define as a sum over all your phase space divided by this Planck scale, and then with a delta function. Okay. If you include delta function, then basically you can sort of already absorb this delta is already in the limit of this delta equals to 0. Okay, so now if you have two systems, they can exchange energy. Okay, but their total energy is E, so that means E2 is E minus E1. Right? So independently, I can write the omega function for system 1 and system 2. Okay, so now is to have an expression for the omega function of the combined system. Okay, so now by definition, this should be the same as P dq okay. So now basically I assume those two are independent. So that means my total Hamiltonian is nothing but the Hamiltonian of system 1 plus the Hamiltonian of system 2. Okay, so basically I want to show that this is equal to something like, okay, so suppose, how do I count the number of different configurations for my total system? Okay, so suppose my system 1 has energy E1, and so it has omega 1 different way. At the same time, my system 2 will be at the energy E minus E1, right? So the system 2 has omega 2 E minus E1 different way. So you should multiply them, and then you should sum over or integrate over all possible E1. So I want to show this. Okay, so by the definition. By using the definition. Okay, So that's very simple. So this integration has two parts. So you must integrate no, sorry, here. Okay. So this integral over P and Q, you can separate that into the integration of P1, Q1, and the integration of P2 and Q2, right? And then you have this okay. And I'm going to do some treatment for this term. Okay, so I'm going to write this H. Okay, so this is E minus H1, P1, Q1 minus H2, P2, Q2. Right? So that means I can write this as the integration over D1, E1 minus what do I want to do? Let me see, what do I do wrong here? Let me see. Okay, so that I want to prove that oh, sorry. So okay. And okay, so then this energy has a component E1 minus E2. Okay. I want E1. Okay, I know. Okay, sorry for the delay. Okay, so I want to write in this way. I want to write this. I show you this. Okay, so I want to replace this term by this. Okay, so why can I do that? Okay, so this is integration of a dE1 with two delta functions, right? So let's just apply delta function rules. That means if I can think about this term. So this term means that when I integrate over E1, I can replace everything E1 by H1. So here means E1 I can replace that by H1. Okay, so it's going to replace here. Okay, so if I do the integration, then what I'm going to get is E minus H1 P1 Q1 minus H2 P2 Q2, which is exactly E minus H. Okay. So this delta function, I decompose that into integration of d with a two delta function. Okay. So now I move this integration of d outside. So what you get is dE1. Now I can separate the integration of some P1 and P2. Okay, so one of the delta function only have this. Another integration right? So this is nothing but my omega E1, and this is nothing but my omega E2, which is omega E minus E1, right? So that means I can prove, which is the same as the formula we want to prove. Okay. So this is something also basically the application of the delta function. Okay, so how do I remember this? Okay, so remember the trick is to just think about the discrete version first, and then convert that into the continuous, then use the delta function. Okay. Okay, so basically, if I have a random variable s and then random variable y, and they are discrete. Okay, so I basically put the sum, for example. Okay. Okay, so what is the probability of s? Okay, so basically you sum over all x, sum over all y, right? So then basically that you create the xy pair with this probability, right? But this will only contribute to this s if this sum happen to be x. Okay, so this is discrete version which you can easily convince yourself. Okay. So now to convert this to a continuous version, the only thing you need to do is you convert the summation to an integration, and then you convert a discrete delta function to the continuous delta function. Okay, now but remember there's a minor difference between those two. Here, in the discrete version, PB, it means the probability. And here, this is a probability density. Okay, they sort of have a different unit, right? And that's taken care of by this delta function. Okay, so the certain property of the delta function is to take care of this the unit involved in this formula. Okay, but so if you cannot remember or derive this the continuous version, okay, so it basically is simple. It just it's easy to rederive the discrete version, and then you just convert this to a continuous version. Okay, so now the next is one of the homeworks is about the triple product relation. Okay, so basically we start from dE is TdS minus dV. Okay, so basically this is the energy conservation, right? So this is energy change is this is a dQ and this is a work. Okay, so you can remember from an energy conservation to get this. Okay. Okay, so now in this kind of expression, it basically I put the left hand side as a function of the right hand side. Okay. Then basically I will get what is the T is partial S partial V and the minus P is partial V. Okay, so here you keep the another sorry. So T would be partial E partial S, then you keep V fixed. And minus P would be partial E partial V, where you should keep S fixed. Okay. So what's a triple product relation? Okay, so you can start from a relation something like that. Okay. So this n can come from something that I think f is a function of x and y. Okay, and if I get this relation, then that implies certain relation in the partial derivatives. Okay, so first on the left hand side, this should be 1. Okay. Okay, so if I want to express f as a function of x, y, then what I should do is divide everything by c and move other term to the right. So what I get will be df is minus a divided by c dx minus b divided by c dy, right? So that means my partial f partial x fixed y equal to minus a divided by c, and the partial f partial y fixed x would be minus b divided by c. Okay, but I can also imagine this as a sort of change the independent variable. I can think about x is a function of f and y. Okay, so to do this, basically I put x on the left and divide the prefactor, so then I get dx is b divided by a dy minus c divided by a df. Okay, so that implies partial f and no partial x partial y fixed f is minus b divided by a. Partial x partial f fixed y is minus c divided by a. Okay. So then what do I want to write? Let me see. Then what why do I? So then let's try this. So what's partial f partial x and partial Okay, so basically I want to find something like that. Okay, so partial f partial x is a minus by c. Partial y partial f. Do I have this? Okay, and partial x partial y. Partial x partial y is minus b divided by a. Okay, so I don't have directed this, but this can be basically here. If I fix the same, then basically I do this inversion. This okay, so that means it's b divided by c. Okay, so now if you see that everything cancel, you get the minus side. Minus 1. Okay, so it's sort of simple. So if you are comfortable with this kind of relation, then you can basically the rule is just you put whatever you want to be the dependent on the left and divide by prefactor. On the right, you have variable that you think they are independent variables. Then you can get all your partial derivative. Okay, so by arranging two different things on the left, you can get different combination. Then from those, but they are only independent ABC. There are only 3 degrees of freedom, and there are many possible partial derivatives. So they must have some relations. Okay, so this is one of them. Okay, so more physically, if you want to think about this S as a function of E and V, right? So that means in the dimension, so you can think about 3D plot. So this is the E, this is the V, and this is S, right? So you can think about SEV equal to a constant. So this will be a surface, right? So suppose this is a surface. So this surface is SEV equal to S0. Okay, so now let's start from somewhere that is E0, V0, and S0. Okay, so then I can do different things. Let me see. Do I want to change my volume to? No, I don't. Okay, so no, this is not a service. Okay, so suppose I start from somewhere that is E0, V0, S0. Okay, so then I want to, so but this S is a function of E and V. Okay, so I first go on a row that the S is a constant. Okay, so I go here, and then I go here with a constraint that E as a constant, and I go back with the V is constant. Okay, and I adjust so that it go back to the original point. Okay, so here basically I increase my volume, so my volume become V plus dV0. Okay, and then here I change my volume back, so I back the minus dV0, so I go back to V0. Okay, and then now I go back here at the last trip is V constant, so I'm at V is go back. Okay, so how do I describe? So this process, so I start from E0, V0, S0. Now S is a constant, right? So I require that volume increase by delta V, and S doesn't change. Okay, so then in this way I can calculate change in ES. That will be E0 plus partial derivative, because now I change V, right? So partial E, partial V, and I fix S constant, and my V change to delta V. Okay. And now the second step, my E is a constant, and I have a minus delta V difference. So that means my E does not change. So I just copy my original E. And V changed by minus dV, so I go back to V0. Now my entropy should change, right? So the entropy changes. Now the change of variable is V, where I fix E constant, and then minus delta V. Okay, so now the last step, I have a V equal constant, and I require my delta E is exactly this one, so I go back to delta E is minus partial E partial V as delta V. Okay, so that means I go back to, I enforce myself to go back to E0 and V0. And what's the S? So now S will go from this one plus partial S partial E and delta E, right? So delta E, I can use this one. Okay, so basically I can require this to be S0. Okay, so that means those two terms add to 0. Okay, so if I write them, so that means minus partial S partial V E delta B minus delta S delta E V delta partial E partial V S delta V equal to 0. Okay, so now I can cancel this delta V. Okay, so that means partial E partial V S partial E, no, partial S partial E V divided by partial S partial V E is minus 1. Okay, but as I mentioned here, I can write this as the 1 over partial V partial SE, right? So then I get again my triple product relation. Okay, so it just means you can either do a very mathematical derivation, start from these so-called differentials, or you can think about a more physical process that you go from S0, EV, E0, V0, and you go have 3 steps. The first step has the entropy constant, the second step has the energy constant, the third step has volume constant. But you manage that you go back to the origin point. And in order to be consistent that you can go back to the original point, you must satisfy this triple product relation. Okay. Okay, so let's take a break and be back at around 2:20. Okay, so let's continue. Okay, so I have one more homework project that we want to go through for today. So it's about probability distribution. Okay, so three different kind of typical probability distribution that we will encounter in StatMech or other part of physics. The first one is the uniform. So uniform distribution usually has a lower bound and the upper bound. So I can think about this is from 0 to 1. Okay, so that means if it's a constant, okay, so it's 1 actually, 0. This might be counterintuitive. Why it is 1? So it's a constant. So the question is why this constant is 1? Because it satisfies the normalization factors we will see in a moment. Okay, and it's related to the range. So now here I say range is between 0 and 1. And it's 0 otherwise. Okay. So first I check normalization. So the normalization is 0 to 1 probability rho x dx. I want this to be 1. Okay. So it's very simple. So suppose this is a constant, then it's a c dx. That is c and equal to 1. So that means c equal to 1. Okay, then I can calculate the probability between certain region. So this is the constant is the probability density. So I can, what's the probability of 0.7 to 0.75? And that means I integrate from the 0.7 to 0.75 my rho x dx, and will be 0.05. Okay, so now this 0.05 is a number. Okay, so another typical one is the exponential. Distribution. Okay, so this goes to, and the x has to be, so usually this is what you think about in t, or you can, it's x, doesn't really matter. So for t positive, so that is something that for positive number is exponential decay. Okay, so you can ask what is the probability that is about 2 tau. Okay, so the lower limit is 0, upper limit is infinity. Okay, so the probability for exponential probability distribution applying from 2 tau to infinity is the integration from 2 tau to infinity. Okay, and then let me see. I didn't normalize this properly or not. Okay, so I have this. Okay, so let's check this normalization first. Okay, so let's check the normalization of this exponential function. Right, so no, do I need to do that? Oh, yes. Okay. So there will be et 0 to infinity 1 over tau is minus t divided by tau d tau dt. So this integration is simple, right? So it's nothing but a yes. So you go from with a minus. So that will be minus 0 minus minus 1 will be 1. So it's properly normalized. Okay. So you should, for every probability distribution, you should try to check the normalization factor. Okay, so then in this way, I can calculate what's the for exponential distribution. What is the probability that happen between 2 tau to infinity? Okay, so exponential decay means like it only happens in short time, right? So that means if you are 2 tau away or more than 2 tau away, it should be small. So we should expect this is not a huge number. Okay, so that means you integrate from 2 tau to infinity. So it's exponential minus 2 tau divided by 2. So it's minus 2. Okay, so which is 0.135. So it's not a big number. Okay, so that means this tau is like the time scale. So if you are 2 time scale away, then you have only like 10%, 13% probability up to infinity. Okay, so most likely with 90, around about 90%, which should happen within the 2 tau. Okay, so then and another one is the Gaussian, right? So Gaussian basically is something you can think about the velocity distribution. So basically it's a v squared. And then you divide by some standard deviation square. And this will determine the normalization factor. Okay, so you can check yourself that this is normalized. Okay, so now here this v go from minus infinity to infinity. Okay, so again, you can check what is the probability that you are more than 2 sigma away from your center. So that means you basically need to do this integration. Okay. Okay, so now if you rescale this, okay, and also you think about this something that go from infinity, go to from 0 to infinity. So we'll go 2. Right. So this is basically half of your normalization. So you got something that is 1/2. Okay. And this is related to so-called error function. Okay. Okay, so you can look at the table. So usually there's a table or some program that you can calculate this error function numerically. And then what you can estimate that this is about 0.03. Okay, so that means also it decay very fast, right? Okay, so what is the mean? Mean, that is you integrate over your probability density and multiply by x and dx, right? So for uniform, 0 to 1, and your row x is 1, and you multiply by x and dx is 1/2, right? So it's very intuitive. So you have a uniform random number from 0 to 1. Your average should be 1/2. Okay, and now for exponential decay, you integrate from 0 to infinity. Your probability, your t multiplied by rho t is 1 over tau exponential minus t divided by tau dt. Okay, and then you just do an integration, you get this is the tau. Okay, so now remember that we in the previous hour we already mentioned this, right? So from discrete to continuous, so if z is x plus y, okay, so the probability density of z will be dx dy probability densities of x multiplied by the probability density of y multiplied by a delta function z minus x minus y. Okay, so now I can write this as sort of a convolution because z is equal to x plus y. So z minus y is equal to x. No, sorry, no. Now, so if I do integration over y, so I can use a delta function, right? So I have a integration over y, and I have this delta function, right? So that means I should have y become z minus x. So what will happen is something like this. Okay, so it's sort of a kind of like a convolution integral of rho x and the rho y. Okay, so now if you think about a velocity, so then it's a Boltzmann distribution. So that means what's the probability density of Vx, Vy, Vz? So each one has a right? Okay, so I can calculate what is Vx squared average. So that means you have dVx, dVy, dVz, Vx squared. Right? So it only give you basically two of the integral over dy and dz, vy and vz basically can give you one. Integral over vx give you basically standard deviation, and that give you kt divided by m. Okay, so that is our equipartition principle, right? So 1/2 minus 1/2 m bx squared is basically half of kbt. Okay, so now you want to calculate what's the probability density of certain velocity magnitude, right? So what's v? V is the square root of vx squared plus vy squared plus vz squared. Okay, so now I want to transform from my original. So I can think about this is they are independent. Okay, so they are independent, so it's actually vx multiplied by rho vz. Okay. Now I have this function. So what's the probability function of this certain velocity magnitude? Okay, so now I just use our delta function formula. Multiplied by a delta function. Okay, so the advantage of a delta using delta function is very easy to write down the formula. Once you know how you want to transform your variable, you can write down the formula immediately. Okay, so that you just need to learn how to calculate the delta function. Right? So you just plug everything in, right? So that I can make them symmetric. So it's something like because vx squared plus vy squared plus vz squared will be v squared. Right? Okay, so now this integration, I can change this integration to the integral over three-dimensional spherical coordinate. 0 to pi 2 d theta, 0 to 2 pi d phi, and 0 to infinity v squared sine theta dv, right? Okay. So now this is theta only integrate over this sine. All right. So this one give so this all integrate over 2 phi giving 2 pi. Integrate over theta give us cosine theta 0 and pi. And integration over v, okay, which you can carry out. Okay, so it's simple because you have a delta function. what you have is just reply everything by V. Okay, and if you clean it up, it will be something like this. Okay, so I would recommend you to get familiar with writing down the probability transformation using delta function. Okay, so it's very convenient. Then once you know how to calculate delta function, you can easily calculate many quantities. Okay. Okay, so that's the part I want to review about some of the homework. So in the next week, we'll continue to review some other homeworks. So now let's go back to our okay. Okay, so before the midterm, for the midterm, you should understand three examples. Okay, so here basically you have an isolated system with E fixed. And in canonical and grand canonical, you think about total E fixed. Okay, but you think about one of them is best, one of them is system. So actually, also particle number is fixed. Okay, so now in canonical ensemble, they are allowed, the system and base, they are allowed to exchange energy. Okay, and in grand canonical ensemble, they are allowed to change energy and the particle. Okay, and if they exchange the energy, then the temperature should reach equilibrium. So the base essentially defines what's the temperature. And in grand canonical, your base basically will determine the temperature and the chemical potential. Okay, so there's a dual. So energy, temperature, particle number, chemical potential. Okay, so in canonical ensemble, the most important thing is entropy, which we calculate from Kb log of omega function. Okay, so that's basically our essential point in the microcanonical ensemble. And In canonical ensemble, then we talk about partition function. Okay, so now if you have a state with energy E, then the probability is proportional to x1 minus En divided by kBt. Right? So remember now I assume the base is huge. So even though my system can exchange energy with the base, the temperature, the base is so large that the temperature is I can assume the temperature remains the same. So T is fixed. Okay, so in that sense, if I have a state, particular state with energy En, then the relative probability will be proportional to exponential En minus kBt. Okay, so then in order to normalize my probability, then basically I have a partition function. Okay, so that's sort of I normalize my partition. So I probability proportional exponential minus En divided by kBt, right? So I sum over all possibility, then I can get my normalization factor. So that means my probability is 1 over z log En divided by kBt. Okay. And from the log of the partition function, I can calculate many things. For example, you can easily convince yourself that energy exploitation value is nothing but the partial derivative log of a partition function divided with respect to beta. Okay, so the trick is I have this log. So when I take a derivative, I get 1 over z. So that's my normalization factor. And then I have a probability multiplied. Then this beta will bring down this energy. So I can get energy exploitation rate. Okay. And for this partition function, then basically I can define a free energy. Okay, so in this case, it has a name. It's a Helm. Right? Okay. And that's connection to our thermodynamic function that you can show that this is nothing but E minus Ts. Okay, so this relation is important for us to calculate all the relation. Okay, so let's go again. So remember, we can start from energy conservation. Okay, so when I only have entropy and heat and P and volume, then this is nothing but T ds minus P dV. Okay, now if you can change your particle number, then I add in one more term that is mu dn. Okay. Okay. So for microcanonical ensemble, our important I calculate entropy. So I move entropy to the left. Okay. So as we mentioned before, now with this kind of expression, you can relate different quantity by partial derivative. So that means once you know the entropy, so now this entropy will function of energy, volume, and particle number. So that means 1 over T is partial S partial E. P divided by T is partial S partial V minus mu divided by T is. Okay, so how is this Helmholtz free energy important? Because if I divide A equal to E minus Ts. Okay, so the important thing to find is what is dA. So dA is dE minus T ds minus S dt, right? Okay, so now I can use this expression for the dE. Okay, so we see that TDS got tensor, so it becomes minus S dt minus P dV plus mu dN. Okay, so that means I can think about my free energy as a function of T, V, N. Okay, and my entropy is partial A, partial T, pressure is partial A, partial V, and chemical potential is partial A, partial A. Okay, so I'm lazy, so in principle, you should write down what other variables are kept as a constant, right? For example, V and N. Okay, so sometimes you got lazy, but you should remember that there are things that you keep the constant. Okay. Okay, so now another important trick is sort of uncoupled system. Okay, so for canonical ensemble, you can think about I have a huge bath. Then I have many systems. Okay, so each one of them can exchange energy with your base, but they don't talk to each other directly. Okay, so there's no direct interaction between those two. Okay, so in this sense, the system total energy is summation of the subsystem energy. Okay, so in this case, the partition function is the partition function of each one product, and the free energy is the sum of each subsistence subpartition sub free energy. Okay, so this can be convenient in calculation, as we will see later. Okay, so now usually the first important step is to understand micro-canonical ensemble. Okay, but it's usually not very easy to do the calculation. Okay? So in reality, usually we keep temperature as constant and chemical potential as a constant. So that basically does the concept of canonical and grand canonical ensemble. Okay, so important step is this. Okay, so once you have understand this, the other is a simple generalization that you allow more quantity to exchange with the base. Okay, so now you can go basically the same thing. Suppose you have a state with index small n. Now because your particle number can vary, so you have to let me know what's the energy associated with this state and the particle number associated with this state. Okay. So again, now it's similar. So this relative probability, you have the same energy factor, but you have to subtract the energy by the mu n, mu capital particle number multiplied by chemical potential. Okay. Now then you can do the similar thing. So you can define a grand canonical partition function. Okay, so I can use this symbol. Or this symbol. And it's sum over all possible states. Okay, so you can see this construction is very similar. Okay, so basically you know that your degree of freedom. And then you know the relative probability. Now you want to normalize your relative probability, so you get your partition function. And then you put the normalization, so you can know exactly the probability density is 1 over your partition function and your relative. Okay? Okay? And then you can calculate the grand canonical free energy. Okay, and it's going to be E minus Ts minus Un. Okay, so you see here, you start from something that is energy. So you exchange energy, so you have a Ts, and you change particle number, so you can have mu n. Okay, and this under certain most usually correct assumption, this is minus Tb. Okay, so now you can also think about uncouple the grand canonical system. So it's similar. So each system, they can exchange energy and the particle number. Okay, so in this case, their grand canonical partition function is the product for each subsystem, the grand canonical partition function of each product, the subsystem. Okay. And formally, there's a relationship between the grand canonical partition function and the canonical partition function. Okay, so basically, grand canonical partition function, you can think about, I can sum of m. M is your specific particle number. And you have, for each m, you have certain energy levels. Okay. So there's a mu n. So I take this mu n out, m divided by kBT. Okay, so if you look at this inner sum, this is nothing but the partition function at a fixed particle number m. Okay, and furthermore, you can exponential this using the, so partition function take a log will give you the free energy. So or you take an exponential of the free energy, you get the partition function. So that you can think about. Okay, so this is the grand canonical partition function. Right? So you have a different possible particle number. Each of them you take you calculate the free energy, and you also particle due to a chemical potential, you have some other exponential. You sum of them, and then you get the average. You can basically you get the grand canonical partition function. Okay. Okay, so that is sort of the key point for the up to Grand canonical partition function. Okay, so in next week we'll talk about more example, maybe some problem set related to canonical and Grand canonical partition function. Okay, but for the last hour for today, we will move on to the chapter 7. So basically, we want to spend some time to understand how to describe the quantum mechanics in non-zero temperature. Okay. So now let's take a break and let's be back at the 3:15. Okay. Okay, so let's start. So now if you try to think about what you have learned in your first year graduate level quantum mechanics, so essentially it's the zero temperature quantum mechanics. Okay, so you learn about a wave function of bracket. Okay, so essentially what is important is the wave function square is the probability distribution of that wave, right? So for example, the wave function square give you the probability density. Right? Okay, so then you talk about or you have some Hamiltonian. Okay, so you think about that's an operator, and then you try to find the eigenvalue or eigenfunction of that operator. Something like this, right? And then you have a superposition principle that an arbitrary function can. So this, if you have a set eigenvalue, then you have a so-called the basis. You can represent any function, any wave function as a summation. Okay, you can use this eigenbasis to with a superposition to describe any wave function. Okay, and then you have so this is static, and then you have the Schrödinger equation, right? Schrödinger equation says if you have basically you have you have a Schrödinger equation, so you can calculate this, and so that's why we want the eigen function, because well then if this is eigen function, then this is easy, right? Okay, so I'm sorry, I'm maybe switch between the bracket notation and the wave function notation. Okay. So that means if I have an eigenfunction, okay, so that means for for eigenfunction, the time evolution simply give you a phase. Okay. So then by decomposing into eigenfunction, then you can solve this also dynamics. Okay. So then you may wonder there's no temperature anywhere. Okay. So now think about a classical mechanics. Okay, so we mentioned that just think about canonical ensemble. So suppose I have a state energy En, so the probability is proportional to the Boltzmann weight. Right? So that means if my T goes to 0, okay, so now I can assume all the energy I sought. Okay, so I can 0 smaller than E1, smaller than E2, and all positive. Right, so I can shift my energy. So all my energy are positive, and I have a ground state energy. Okay, so I can set that to be 0. Okay, so that means when the T go to 0, basically the ground state has the largest probability. So everything, so basically the ground state probability goes to 1. And the excited state probability goes to 0. Okay. However, for the non-zero temperature, I have all these probabilities. Right? So E1 was something that has something that proportional to so the point is, in classical mechanics, when I have non-zero temperature, that means I have sort of a probability distribution between state with different energy. Okay. So as I lower the temperature, the low energy state become more and more important. As I go to 0 temperature, I only care about the ground state. Okay. So now if I want to have similar thing in quantum mechanics, then I need to have a mixture of states. Okay. However, it's very confusing in quantum mechanics because in quantum mechanics, I also have superposition. Okay, so it's perfectly okay in quantum mechanics that I have a state wave function that is a superposition of my ground state and my first excited state, right? Right, we are doing this all the time, right? So basically, I decompose any wave function as the superposition of my energy eigenstate. So basically, I'm writing some kind of summation of my energy state. So this is called superposition. Okay, but then in the end, I got a single cat, or single wave function. So this is so-called superposition. Okay, so now the main question is, what is the difference between the superposition and so-called mixture? Okay, so to understand this, we need to understand how do we calculate the expectation values. Right? So in quantum mechanics, to calculate the expectation value, if I use a bracket notation, then and of certain operator A, right? So basically what we do is, if we use bracket, then I just bra operator and A and cat. Okay, so if I use the coordinate representation wave function, this is something like okay, so now let's write down what happens if I have a superposition of two states. Okay, so first I need to find a corresponding bra, right? I need to cat become bra, and I coefficient have a complex conjugate. Okay, so now if I want to calculate expectation value of a certain operator of this superposition wave function, then I got this, right? So you can imagine you have four terms. Plus alpha star. Okay, I will have four terms, right? Okay, so that you should have learned this in your quantum mechanics. Okay, so if you talk about quantum mechanics, you learn that many things come from the interference, and interference come from those cross terms. Okay, so this, so we call this sort of coherence between your two different wave functions. Okay. Now, if I want to, now let's think from a different way. Suppose I have a, and remember this wave function is normalized, so that means alpha squared plus beta squared is 1. Okay, so now if I do a slightly different thing, if I think about I have a probability alpha squared, Okay, so now it's we will see the crucial difference. So now this is the classical probability. Okay, so in quantum mechanics, you have a sort of intrinsic probability due that, for example, show up in Heisenberg uncertainty principle. Okay, so when you perform a superposition of two wave functions, you got a new wave function. And this new wave function still has to satisfy uncertainty principle. And when you calculate the probability density, you still have some intrinsic probability density associated with this new wave function. Now, if I ask you, as I put this in a slightly different way, I have a certain probability the system at the wave function 1 and certain probability system at wave function 2. Okay? So then you can ask again, then what is the expectation value of A? Now this expectation value of A has two stages. The first stage has a probability, classical probability. So your probability, you have a classical probability. So the system has a probability alpha squared to be in wave function 1. Okay? So if the system is in the wave function 1, the expectation value of the A operator is psi 1 A psi. Correct? So this is the quantum. And this has contained certain intrinsic quantum mechanical probability. And if the system is in wave function 2, then you have a different quantum expectation value. Okay, so then I'm going to say that my expectation value is going to be okay. So I have a two stage. First stage, I have a classical probability. I have alpha squared probability to be in system 1, wave function 1, and have a beta squared probability in wave function 2. If I in the wave function 1, then have a quantum probability expectation value that have bracket psi 1 A psi 1. If I am wave function 2, then have this bracket psi 2 A function psi 2. Okay? So now the crucial difference to see what's the difference with this formula with the superposition. Okay? So if I superimpose two wave function, then I got a new wave function, a single wave function. Okay, so if I do the expectation value of this new wave function, I will have interference term or coherence term. Okay. If I have a mixture of two states, then I don't have this cross term. Okay, so that is the crucial difference. Okay, so basically, I'm going to define my expectation value as a sum over all classical possible. So this PM is some kind of classical probability. Okay, so I have n different possible states. Okay, and for each possible state, I have the quantum expectation value. Okay. Okay, so if you so this is called mixture, but I should contain my original. Okay, so the thing is, so for each term, okay, so each term, each possible state in the mixture can be written as a superposition of other bases. That's fine. This is okay. But somehow I should be able to write as a sum. Okay. So if I only have one term in the mixture, that means I do not mix anything, right? So it's called pure. Okay, so the mixture is n go to from 1 to certain, say m, right? So when m is equal to 1, that's it's a pure state. Then you don't need a summation. So one state, one possible state with probability 1, then you go back to your original definition. Okay. Okay, so it's important to remember if you have a two state, then you can have a classical mixture of two states, and then you can have a quantum superposition of two states. They mean different things. Okay, that's this distinction you need to know. Okay, so here then usually you will encounter so-called density matrix operator. Okay, usually it's called rho. Okay, so how do I define this? So start from our definition of the expectation value of a mixture. Okay. So in quantum mechanics, when we want to solve a problem, sometimes I just pick certain bases. Then my Hamiltonian become a matrix. And then I can diagonalize this matrix. Okay? So it's important or convenient to pick a certain good basis. Okay? But also sometimes I want to write the expression in a basis independent way. Right? When you write down the Schrodinger equation, you don't need to specify the basis. Okay? But when you do the calculation, sometimes you prefer to fix certain basis. Okay? So now I just pick any basis you like. Okay, so the one important property of basis is the identity operator can be written as this. Okay, I'm sure by now in quantum mechanics you know this important decomposition of the identity operator in terms of the certain basis. Okay, so now I want to insert this. So I just put identity here. Okay, so once I insert identity, then I sort of break my bracket into a product of two bracket, right? So one have this bracket, this bracket. Okay, so remember that once they are in this bracket, basically they are numbers. So they commute, right? So one of problem of a quantum mechanics, if you are dealing with operator, they don't commute. Okay, but if you have certain bracket that already put the bracket operator into some certain expectation value and it's a number, for number they commute. Okay, so then I'm going to move this to the left and this to the right. Okay, and so basically I have rearranged this. And so okay, and also I have a two summation, so I put the summation of alpha out, and here I put a summation of alpha n here because okay, so you should go home and check this formula. Okay, so once I'm done with this rearrangement, I find this, so I define this to be our density operator. Okay, so then I can write the expectation value as a sum over a complete set sandwich and A and multiply another operator row and this. Okay, so I know if I have a bracket sum over complete the basis, that means trace. Okay, okay, you think about I sandwich my operator with some basis. If I put phi I, phi j, then I get some matrix psi ij, right? So now it's psi alpha, so it's a matrix alpha alpha, and then sum of alpha. So that means in terms of matrix language, it's a trace of the matrix. So this is usually written as the trace of A multiplied by my density matrix operator. Okay, and what is my density matrix operator is sum over this. Okay. Okay, so in a sense, this is a generalization of my expectation values. So first, we can start from a pure state. So remember that if I have only one term in my mixture, that means I'm in pure state. So that I have only one wave function. Okay. If I have only one term, so that means my pure state. So that I have only one wave function. Okay. So remember that if I have only one term in my mixture, that means I'm in pure state. So that I have only one wave function. Okay. If I have only one term, so that means my have a probability 1, I have to be, let's just call this state one wave function. Okay, so that means according to this definition, my expectation value will be trace a rho, which is a trace of a. Okay, so now you can revert the process. Now trace, according to our definition, is sum over certain complete basis. Okay, so now I can revert this process to get the identity. How do I get that? So then again, I switch those two, so I can get this. Right? But this is nothing but my identity, right? So that means this go back to. Okay, so the important things for any definition of the mixed state or density matrix operator, if you only have one term, you should be able to show that you go back to your typical quantum mechanics pure state calculation. Okay. And pure state has certain property. Okay, so this is a pure state density matrix. It's only for pure state density matrix that if you multiply by itself, that is rho square. By definition, you get this. Okay, so I assume my wave function is properly normalized. So this is 1, so you get back. So if you square the density matrix, you go back to yourself. Okay, this holds only for the pure state. Okay, so if you have a mixed state, then if you take a square, then usually it's smaller, it's different from your original one. And you can also check the normalization of the density matrix. Okay. Essentially, this will become this 1. Okay, you can work out the algebra yourself. Okay, so once I have a density matrix for any operator, the expectation value is something like this. Okay, so now if you want to switch back to a coordinate representation, then you can write. Okay, so this is a base independent hop, so you pick up bases. Right, so basically you can have a matrix Ij that is something like. Okay, so and if you have a coordinate basis, for pure state, you can think about you have a Q prime, which is Q. Right, because I know this is my wave function, and this is my wave function conjugate. Okay. So you have a okay. So how does this help us? This we can write down because now we want to generalize our description for canonical and grand canonical ensemble to the quantum mechanics. Okay, so now first canonical. Right? So that means my canonical ensemble, the system is described by a canonical density matrix, which can be written as 1 over the partition function. I know this just give me my. So how do I do that? So remember, classically, I have a weight that's exponential minus beta e divided by partition function, right? So now this is intuitive. If I have an eigenenergy basis, okay, so right in quantum mechanics, the energy basis is somehow special because it's the eigenstate of your Hamiltonian. So suppose eigenenergy basis, I know this, then it's intuitive that non-zero temperature means I have a Boltzmann probability for each energy eigenstate, right? Okay, so if you put that into the picture definition, that means I have this Boltzmann probability, and then I multiply by this En. Right, that's it. Okay, so in this case, I can rewrite this partition function. Okay, so it's nothing but again the sum over all the Boltzmann weight. Okay, but somehow I want to generalize it. I want to write this expression in a way that is independent of the basis. Okay, so the first step, I can intuitively get this. The second step, now I convert this normalization factor, which is my partition function. Then I can think about this is nothing but sum over the energy expectation value. If I sandwich my Hamiltonian with an energy eigenstate, I get the energy, right? So if I sandwich exponential minus beta h with my energy eigenstate, then I get energy En. Okay, so you see we can get this, and this is nothing but the trace of the exponential minus beta h. Okay, and now we look at this factor. I can write this is okay. If you think about this, what's this operator? This is nothing but my exponential beta h, right? Okay, so this is nothing but my exponential beta h. If I project this to the eigenenergy basis, I got this expression. Okay, so combine all this observation, I can say my canonical density operator can be written as in the basis independent way exponential minus beta h over trace. Okay, so this is very simple. Classically, exponential minus beta e, right? So now here, quantum mechanics, you have all possible e described by your Hamiltonian. So it's exponential minus beta h. Okay? And you want to sum over all possible energy that you can take a trace. of this operator, then you sum over all possible energy. Okay, once you have this, for example, then you can get the entropy by our definition of KB trace rho log rho. So practically, you will think about this rho as a matrix. Then you know how to operate rho log rho. Let me see. Okay, so we will quickly introduce. So now if I have a quantum simple harmonic oscillator, okay. So now all we need to know is the energy levels. Okay, in quantum mechanics, you learn how to solve this problem. I know the energy level is n plus 1/2 h bar omega. Okay, essentially that's all I need to know to write down the quantum mechanical partition function. Okay, so essentially if you know all the energy level, then you can write down the partition function and you can get everything. Okay, so that your partition function is sum n go from 0 to infinity exponent beta En, right? Well, and this sum is easy. This is something like okay, so essentially here there's not much difference. The only thing is the quantum mechanics is it now became a problem that you need to solve for energy eigenstate. Okay, so if you know how to exactly write down the eigenenergy state, then all the calculation is also similar to the classical one. Okay, but now I can follow my recipe. For example, what's my energy exploitation value? I can calculate by partial log z partial beta. Right? Now I have a z, so I can get this. Log z will give you 2 terms. Alright, you take a derivative, you have 2 terms. One term is from your 0-point energy. Okay? E. So you have 0-point energy plus this. Okay? So I can interpret this is my average occupation number, right? So then this is h bar omega average occupation number plus 1/2. Okay? And then you can also calculate the specific heat, everything. Okay, so the key point for today is to understand the definition of the mixture. Okay, so you have a probability over all density single party. So you have a classical probability over different states, and each state you have a density matrix operator, and you have a classical probability sum of those different density matrix operators. Then you get the quantum density matrix operator at non-zero temperature. Okay, and you should. Okay, but if you know the energy level, then the calculation will be simple. It's similar to the classical one. You just sum over all possible states. But sometimes you don't know how to solve for the exact eigenenergy, but you can still write in a formally you can write a partition function as exponential minus beta h divided by the trace of exponential by the beta h. This will be the starting point of many different kind of exact and numerical approximate methods. Okay, and so that's it for today. So next week we'll talk about more. So you in quantum mechanics already know for boson and fermion they have different symmetry property. Okay, so for many particle wave function you need to symmetrize or anti-symmetrize wave function, and that will introduce some extra consideration in our treatment for the StatMech for the boson and fermion. Okay, so I will type in the homework, next homework, and also provide and then send you a notice. Okay. And if you have any questions, please just email me so then I can try to explain in the next class. Okay, that's it for today. See you next week.